Our search for the foundations of consciousness has seemingly reached a dead end. All we've been able to resolve is firstly that the movement of consciousness is fueled by a currency of interaction, and secondly, that each conscious perspective is fundamentally unique. Outside of these two meagre insights, however, the quest remains ongoing. After a lengthy inquiry into the nature of the nervous system, we discovered that the boundaries set by our scientific frameworks are more often abstract lines in the sand, useful for communication and clarification, but never ontologically absolute. This led us to inquire into the intelligence of plants, fungi, and other simpler organisms, but still, our search for final bounds remained unresolved. Via the language of philosophy, we even wandered into the muddy waters of panpsychism. Though it was amid these muddy waters where we stumbled across the universal language of process, highlighting the becomingness of our being, and so to a deeper appreciation for the wholeness of this fluxing cosmic continuum. Inquiring further into the nature of being and becomingness, we then unfolded the history of the wave-particle debate, from Plato through to Einstein. And now, amid this terrain of quantum fields, we now seek to understand the nature of both its uncertainty and wholeness in the hope of attaining a more profound understanding of our connection to it, and also what implications such a wholeness might have on the nature of consciousness, set as it is, within each uniquely finite perspective. So join me as I attempt to unpick the infinities of what is. In the world of classical physics, as defined by relativity, we see events as fundamentally causal and deterministic, bound to local interactions limited by the speed of light. Whereas in quantum mechanics, we find a world that is, in contrast, probabilistic, non-local, and as such, produces instantaneous correlations between events that can be separated by galaxies. So, where, within these vast contradictions, can we locate any underlying nature of wholeness? It has been said that if you wish to learn about something, read about it. However, if you wish to understand something, then it's best, they say, to write a book about it. And so it was that in 1951, physicist David Bohm produced one of the most intuitive textbooks on quantum mechanics, simply titled Quantum Theory. However, it was during the course of its writing that, due to this inevitable heightening of understanding, he found himself becoming increasingly dissatisfied with the more commonly accepted interpretation of quantum mechanics, namely the Copenhagen interpretation proposed by Niels Bohr and Werner Heisenberg almost 30 years prior. Bohm arrived at a time when a newly connected, technologically augmented post-World War America was rediscovering its identity. A period of intellectual cross-pollination affecting all spheres of culture, from politics to the arts and even science. A product of his time, Bohm was well recognised for his ability to cross the boundaries between science and philosophy, referred to by his mentor Albert Einstein as his spiritual son, and by the Dalai Lama as his scientific guru. Thus why, 30 years after the publication of quantum theory, did Bohm find himself writing yet another book. Though this time, it was to have somewhat of a less dry and perspicuous title: Wholeness and the Implicate Order. A book that boldly and exhaustively described the resolutions of this 30-year-long contemplation, In particular, Bohm's understanding that the physical world emerges from an interconnected nature of wholeness. What he identifies is that this wholeness is in fact a defining trait shared equally by both relativity and quantum mechanics. As he says, quote, "They both imply the need to look on the world as an undivided whole, in which all parts of the universe, including the observer and his instruments, merge and unite in one totality." As to how Bohm's wholeness is represented within relativity, he describes a wholeness in flowing movement, the clues to which can be found in the understanding of light, discussed in the last chapter, in how the nature of energy, light, electricity, magnetism, space and time, and even matter are all various characteristics of that which is one and the same continuum of process and perspective. And in regard to how wholeness is represented within quantum mechanics, well, all we need to do is look towards the particle state of an atom. This so-called particle we often imagine as just another bit of the universe, tied to its own intrinsic nature. But as we also revealed in that previous chapter, this particle state is only an excitation of a field. More confronting still, and the topic that we shall be discussing across this chapter, is how this particle seems only to attain its more familiar characteristics as a result of observation. And therefore, as Bohm points out, quote, "One can no longer maintain the division between the observer and observed. Rather, both observer and observed are merging and interpenetrating aspects of one whole reality, which is indivisible and unanalyzable." Though as we are still on the hunt for the universal boundary of consciousness, we need to ensure that we don't get too carried away with this idea too quickly. As in the world of experimental physics, the presence of an observer does not necessarily imply a conscious being. It can mean that, but it may also simply refer to a device, such as a photon detector. And so, when opening this next can of worms, people have historically been known to bicker and quarrel quite passionately over which quantum machine is actually doing all the work. Because here it is, folks, as promised, the famous double-slit experiment. An experiment that many of you should already be familiar with. After all, it is famous. Unfortunately, however, it's not an experiment that can serve as a linchpin for any argument, simply because it is precisely this aspect of quantum mechanics that physicists still don't understand. Indeed, the results of the double-slit experiment are to a physicist what mobile phones are to the average person. We all know how to use them, but damned if we know how they work. As so elegantly put by Richard Feynman, quote, "We choose to examine a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. In telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics." In 1924, French prince and physicist Louis de Broglie, inspired by Einstein's description of light's wave-particle duality, considered the idea that if light waves can act as particles, so too might particles of matter act like waves. And it was with this hypothesis in mind that Thomas Young's 1801 experiment was resurrected. As with its predecessor, the basic concept is to send a medium, in this case matter particles, towards a barrier perforated by two tiny holes or slits, through which the particle can pass, and then look for the telltale signs of an interference pattern via an external detector. So we begin simply enough by firing a ray of electrons towards the barrier. Rather than two clumps of particles, we do observe the interference pattern, suggesting that our stream of electrons are passing through both slits as a continuous wave. But we need to be sure, so we start to force the situation. First, we slow the rate of firing, sending through only one electron at a time. One electron fired, one spot appears on the final detector. Another is fired and the same thing occurs. But as the data builds up, bit by bit, particle by particle, an image starts to emerge. It's the interference pattern again. Curious. Even though the electrons were fired one at a time, they somehow managed to create a wave interference pattern collectively. It must simply be that the electrons have their own individual wave properties, which allow them to pass through both slits at the same time, thus interfering with themselves on the other side of the slitted barrier just as a liquid might. But again, we need to be sure. And so we set up a second detector, this time set to measure the activity happening at one of the slits. The detector's role is somewhat like an over-friendly bouncer, high-fiving each electron as they pass through, taking note of their which-way information. Run the test a little longer, and it becomes apparent that electrons only ever pass through one or the other slit at any one time. But here is where things start to get weird. For as soon as the bouncer had confirmed which of the two slits the particle had passed through, the interference pattern stopped being added to, and instead reverted to landing in two distinct clumps. In short, the particle's once wave-like path had collapsed into a single definite path. Remove the observation and interference returns, with all its wave-like ambiguity. No matter how we try to attack the puzzle, the observer, conscious or not, always seems entwined with the outcome. And in the decades that have followed, surprisingly few insights have emerged, though not for a lack of trying. The delayed choice quantum eraser is an extended version of the same experiment that further attempts to probe this connection between observation and the disappearance of the interference pattern. Though the experiment's maze of mirrors and beam splitters is slightly complicated, the idea itself is relatively simple. For if it is only the observation of the which-way information, that is, the bouncer's high five, that forces the electron to abandon its wave-like behavior, then delaying the recording of that information until after the particle has hit the first detector should, in theory, prevent the clumps from happening. But of course, it's never that simple. Because regardless of whether the which-way information is recorded at the time of passing through the slit, or delayed to some arbitrary time in the future, even if it's slowed down by a round trip thousands of kilometers long via the use of entangled partners, the subset of detection events whose which-way information does get recorded will always correlate with clumpy particle-like behavior at the earlier detector, whereas the subset whose which-way information gets erased, i.e. never recorded, always correlates with an interference pattern. As if the particle's random chance of being recorded or not had been decided all along. Some will explain this as a branching of many universes. Some, an atemporality of quantum relations. Others state that it's merely an epistemological problem with deeper truths hidden from our view. But regardless of how we try to explain it away, the results are always the same. Be it an electron, a photon, a proton, a neutron, or even a whole atom. Even large-scale molecules containing more than 2,000 atoms, each has been shown to exhibit these exact results. There's even theoretical proposals for extending these experiments to biological systems, beginning with the virus. But surely these large and living systems host a definitive location in space and time before they are observed. As Einstein said, the moon does not simply disappear when we are not looking at it. Einstein and Niels Bohr famously debated their interpretations of quantum mechanics. Einstein, leaning heavily into the epistemological argument, claimed that quantum mechanics was missing a piece of the puzzle, a piece that he would later refer to as hidden variables. That is to say that it is not that particles exist in some weird state of mixed superposition or a fluxing state of wave-particle duality, but simply that their definite states are hidden from us, and that, therefore, quantum mechanics should only be considered a partial statistical description of what was an ensemble of systems. In his correspondence to Max Born, the mind behind the probabilistic interpretation of the wave, Einstein wrote, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice." The famous declaration, "God does not play at dice." A sentiment to which Bohr would later respond, "It is not for us to tell God how to run the world." Bohr also addressed the epistemological issue. However, he did so from a broader philosophical perspective, highlighting the unavoidable relationality of physics. Whereas Einstein took it as given that physics is the study of local, definite objects, Bohr held that physics analyzes only the phenomena arising from our interactions. Since measurement itself defines the conditions under which our physical concepts apply, it is therefore meaningless to discuss the particle's particular set of properties outside of the experiment. Doing so misses the point that concepts like location, momentum, or spin only apply within the context of the experiment. In their famous 1935 EPR paradox paper, entitled "Can a Quantum Mechanical Description of Physical Reality Be Considered Complete?", authors Einstein, Boris Podolsky, and Nathan Rosen confidently declared that, quote, "If, without in any way disturbing a system, we can predict with certainty, i.e., with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to that physical quantity." End quote. Precisely the type of statement Bohr would push against. But given that both Bohr and Einstein's interpretations made no difference to the measurement's results, the debate was eventually abandoned, considered simply an unanswerable quirk of nature, a matter of taste and nothing more. Until, that is, it was shown to be theoretically testable. In the 1960s, after the deaths of both Einstein and Bohr, physicist John Stuart Bell proved that there would be a difference between the two-party scenarios. And, surprisingly, the results ran against Einstein's description of hidden variables. The quantum mechanical picture of reality, with its traits of non-locality, superposition, and entanglement, seemed to best fit the results of measurement. And with that, the issue was reignited, opening the floodgates for new interpretations that would come to challenge our rationality in ways we never before imagined. And so, for an entire century now, the battle for supremacy has raged on, more ferocious than any World Cup and often just as religious. This theatre of war has become littered with quarrelling outposts, each resolute to the dogmas of their own chosen philosophy, built, as philosophies always are, upon the ideas of a few select ideologues, each hoping to be among those who give solution to the most formidable of riddles, that which once straddled between Bohr and Einstein, the measurement problem. a problem which asks, what exactly is measurement? On the surface, this question might seem relatively straightforward, obvious, boring even. For all it seems to be pushing for is a deeper understanding of what is already understood as the observer effect, a term which highlights that measurements are inherently physical interactions and so will always interfere in some physical way with that which we are attempting to measure. Again, this appears to be little more than a technical issue, one that must deal with the problem of our own getting in the way. But it may be more than this, as it's not simply that we are messing up the measurement, but, as Bohr intuited and as David Bohm's wholeness implied, that we are forever implicated within the measurement. Because the question soon arises, where exactly does the measurement start and end? For example, the double slit experiment seems at first to be confined to the particle and the interfering slits. But as the results reveal, we very quickly have to acknowledge that not only are the measuring devices a part of the experiment, but there we too stand, as observers, entangled with the outcomes of every measurement. And so once again, it seems we have found ourselves on the hunt for universal borders. So in order to keep this conundrum in line with our greater narrative, and its ongoing search for the borders of consciousness operating within a wholeness of fluxing reality, let us begin to tease out our insights by now focusing our attention on the measurement problem, asking, why does the wave collapse when an observer measures it? This we shall do in the next chapter by unravelling the interpretations that followed Bohr and Einstein, beginning with those that appear most relevant to our search for conscious intervention, and then we'll highlight some of the more popular oppositions to these interpretations. And though an entire book would be needed to make this list exhaustive, we shall hopefully gain a small peek behind the curtain as a result of our more holistic overview of this wider collective of thought and insight.